In shell sort, the running time depends on the number of increments and their values. Now, the mathematical analysis of this sorting technique is very complex. Based on empirical studies, the performance was found out to be this for one set of increments and this for another set of increments. Now, this is an unstable sort, which means that it might change the relative order of duplicate elements in the sorted output. This is an in-place sort, which means that space complexity is order of 1 and no extra memory is required for performing this sort. Now let's see why shell sort is an improved version of insertion sort. Now in insertion sort we know that there are many movements, and the reason for many movements is that elements are moved only one position at a time. While in shell sort, elements can move long distances at a time. So if an element is far away from its final place, in insertion sort it will have to go one by one, while in shell sort it can jump and go to its final place. We know that insertion sort is efficient when the size of list is small and when the list is almost sorted. These 2 points are the basis of shell sort. In shell sort, when initially the increment is large, size of sublists is small, so insertion sort on those sublists is efficient. When in the final passes increment becomes small, the size of sublist increases, but then also the insertion sort is efficient on the sublists because those sublists are almost sorted. Now let's talk about increments. The value of increments that we have taken in our example are 5, 3 and 1. Now we can take any other sequence of increments. The only condition is that the increment should decrease in every pass, and in the last pass the value of increment should be 1. Now the sequence of increments given by Donald L. Shell was this. We suggested to take first increment as half the size of list and then divide the increment value by 2 in each pass. So if we have 17 elements, the value of increments would be this. We'll have 4 passes and the sublist form would be this. These are the subscripts of the elements. So we can see that in this case, the elements at odd positions and the elements at even positions are not compared until the last pass. They are compared only in the last pass. So this choice of increments is not a good one. In general, we can say that increments which are a multiple of each other, like 1, 3, 6, 9 or 1, 2, 4, 8, are not a good choice, because in these cases the same elements are compared in each pass. Increments which are relatively prime are a good choice. Now a sequence of increments given by Knuth is this: h1 is equal to 1, hi plus 1 is equal to 3 hi plus 1, and stop at hi when hi is greater than n minus 1 by 9. So if we have number of elements is 10,000, then the increments would be this.